When people think about telescopes, the first thing that usually comes to mind is magnification. It's common to assume that a telescope's main purpose is to make distant objects appear larger, so we can see them better. While this is partially true, it's not the full picture. The primary purpose of a telescope is to gather and concentrate light. This allows us to observe objects in space that are too faint for the naked eye. Magnification comes into play after the light's been gathered, but it's not the telescope's main function. Telescopes perform two main tasks: collecting light and focusing it to create a clear image for observation. The key component in a telescope responsible for collecting light is called the objective. This can be either a lens in refracting telescopes or a mirror in reflecting telescopes. The larger the objective, the more light it can gather. Imagine you're trying to collect rainwater. Using a small cup will limit how much you can collect, but using a large bucket or even a swimming pool would let you gather much more. In the same way, a larger objective allows a telescope to collect more light, letting you see dimmer and more distant objects in space. Once the light is collected, it needs to be focused into an image that we can see. This is where the eyepiece comes in. The eyepiece captures the concentrated light from the objective and it spreads across your retina, allowing you to see the image clearly and magnified. The eyepiece also determines the magnification and field of view, how zoomed in the image is, and how wide an area you can observe at once. Many people mistakenly believe that Galileo Galilei invented the telescope, but that honor goes to a Dutch eyeglass maker named Hans Lippershey. Galileo heard about the invention and built his own version for astronomical observations. This early design was called a refracting telescope because it used lenses to bend, or refract, light to form an image. Although Galileo didn't invent the telescope, he made it famous by using it to make groundbreaking discoveries. He observed the moons of Jupiter, the rings of Saturn, sunspots, and the phases of Venus. These observations changed our understanding of the universe. Early refracting telescopes, like Galileo's, had several problems. The lenses were heavy and difficult to polish. Worse, they caused chromatic aberration, which occurs when different colors of light bend by different amounts, leading to a fuzzy rainbow effect around objects. Additionally, the glass lenses absorbed some light, reducing image clarity. Sir Isaac Newton addressed these problems by designing a new kind of telescope known as a reflecting telescope. Instead of using lenses to bend light, Newton used a curved mirror to reflect and focus it. This design solved many of the issues with refracting telescopes. Mirrors are lighter than lenses and can be mounted more easily because they only need to be polished on one side. Reflecting telescopes also eliminate chromatic aberration because mirrors reflect all colors of light in the same way. Newton's design set the foundation for modern telescopes. Today, most professional telescopes used for astronomical research are reflectors. They use large mirrors to gather vast amounts of light, allowing astronomers to see very distant or faint objects in space. Some telescopes combine the features of both lenses and mirrors. These are called catadioptric telescopes. They use a lens to correct distortions in the image before it reaches the mirror. This design provides the best of both worlds: high-quality images with fewer distortions. While we're most familiar with telescopes that observe visible light, telescopes can actually detect many different kinds of light from across the electromagnetic spectrum. The electromagnetic spectrum includes different types of light, like radio waves, infrared, ultraviolet, X-rays, and gamma rays. Each type of light reveals different information about objects in space. For instance, stars and galaxies don't just emit visible light, they also produce radio waves, infrared radiation, and other types of energy. Consider the Crab Nebula, the remains of a star that exploded as a supernova. When observed in visible light, we can see the glowing gas cloud left behind. But when we observe it in radio waves, infrared, or X-rays, different details come into focus. For example, X-ray telescopes reveal a pulsar at the center of the nebula, a rapidly spinning neutron star emitting beams of energy. Without these different types of telescopes, we wouldn't be able to detect this important information. Telescopes are amazing tools that allow us to observe the distant wonders of the universe, but using them here on Earth presents a few significant challenges. One major issue is the effect of Earth's atmosphere on the images we capture. The atmosphere is not perfectly stable. It's full of turbulence caused by moving air, temperature changes, and other weather conditions. This turbulence distorts the light from stars and planets as it passes through the atmosphere, making it harder to get a clear image. This is why stars appear to twinkle when we look at them from the ground. The same turbulence affects telescopes, blurring the details of the objects being observed, no matter how much magnification is applied. To minimize these distortions, astronomers build observatories on tall mountains, in remote places far from city lights. High-altitude locations have thinner atmospheres, which reduce the amount of turbulence the light must pass through. By placing telescopes in these isolated areas, astronomers can get sharper images than they would at lower altitudes. Observatories like the Mauna Kea Observatory in Hawaii or the Atacama Desert in Chile are great examples of this approach. These places are chosen because they offer clear skies for most of the year and are far away from light pollution. Another problem caused by Earth's atmosphere is the absorption of certain types of light. While visible light passes through the atmosphere relatively easily, other wavelengths, such as X-rays, ultraviolet light, and gamma rays, are mostly blocked. This is good for life on Earth because it protects us from harmful radiation or turning into the Hulk, but it's a problem for astronomers who want to study objects in space that emit light in these wavelengths. For example, many astronomical objects, such as black holes and neutron stars, emit X-rays that can't be observed from the ground because the atmosphere absorbs them. To get around these limitations, scientists have developed space telescopes, which can operate outside the Earth's atmosphere. One of the most famous space telescopes is the Hubble Space Telescope, launched in 1990. By orbiting above the atmosphere, Hubble avoids the problems of turbulence and light absorption, giving us incredibly clear images of distant galaxies, nebulae, and other celestial objects. The pictures taken by Hubble have transformed our understanding of the universe and have provided detailed images of places billions of light years away. These images have not only captured the public's imagination, but have also led to important scientific discoveries, such as the expansion rate of the universe and the presence of black holes in the centers of galaxies. However, the Hubble telescope is aging and won't last forever. To continue exploring the universe in even more detail, the James Webb Space Telescope, JWST, has been developed. The JWST is designed to be much more powerful than Hubble, with a larger mirror and advanced instruments that can detect infrared light. This will allow it to see even further into space and provide new insights into the formation of galaxies, stars, and planets. One of the main goals of the JWST is to study the early universe, just a few 100 million years after the Big Bang. Because light from distant objects takes time to reach us, the farther we look into space, the farther back in time we're seeing. The JWST will allow us to look back to some of the first stars and galaxies that formed after the universe began. This concept of light taking time to travel is one of the most fascinating aspects of astronomy. Light moves incredibly fast, about 300,000 kilometers per second, but the universe is so vast that it still takes a significant amount of time for light to travel from distant objects to Earth. For example, the light from the sun takes about 8 minutes and 20 seconds to reach us. This means that when we look at the sun, we're actually seeing it as it was over 8 minutes ago. If the sun were to suddenly vanish, we wouldn't know about it for 8 minutes because the light, or lack of it, would still be on its way to us. The farther away an object is, the longer its light takes to reach us. When we look at the stars in our galaxy, we're seeing light that left those stars years ago. Some of the stars we see in the night sky might have already died, but because their light is still traveling toward us, we're seeing them as they were in the past. This makes telescopes, in a sense, time machines. They allow us to look back in time and see the universe as it once was. For extremely distant objects, such as galaxies millions or billions of light years away, we're looking even farther into the past. For instance, the galaxy NGC 4845 is about 65 million light years away. This means that the light we see from that galaxy today actually left it 65 million years ago. If there were aliens living in that galaxy and they pointed a powerful telescope at Earth right now, they wouldn't see humans. They would see Earth as it was 65 million years ago, when dinosaurs still roamed the planet. This idea that we're seeing the past when we look into space is one of the most mind-boggling aspects of astronomy. Well, the Earth-based telescopes face challenges due to atmospheric disturbances and the absorption of certain wavelengths of light. Space telescopes like Hubble and its successor, the James Webb Space Telescope, help us overcome these limitations. These powerful instruments allow us to peer deep into the universe, and because of the time it takes for light to travel, they also let us look into the past. Every time we observe a distant star or galaxy, we're essentially engaging in a form of time travel, viewing ancient light that started its journey toward us long before human civilizations even began. This ability to observe the distant past is one of the most incredible gifts that telescopes give us, opening up a window to the history of the universe itself.